Sorry guys, welcome back. And I just want to make you aware, when you have a double acting thing, and in a double acting reciprocating steam engine, and all what you're basically doing over here, the idea is that we have pressures on either side of the cylinder, right? And obviously in the other engines, we always assume it's at the top. So what you're basically doing here is taking kind of like the difference between the two pressures. Obviously, we're looking at the difference between the two pressures, right? So it's always a positive pressure anyway. So if you have a horizontal steam engine, and how do you know that you need to apply that? This thing what we're going to do is that it says on the cover inside is 550 and the other side is 70. Another one would be the pressure above is 30 kilonewton per meter squared, and the other one 1.5. So are we all happy with that? Do we all know when to apply this thing? Obviously, I haven't shown you, but that's the new keyword, right? Which you're kind of looking out for. Other than that, everything else is really the same in terms of the analysis. Just to FR, which is going to change. Subsequently, we're going to look at this example, which I do, and I'm going to close it off with this example. And when I look at the textbook, most of the examples, it's only starting from number 18 to 21 has to do with the so-called connecting rod analysis. Let me just make sure. Yeah. So that is why I've decided to mostly focus on this now and not worry about the equivalent dynamic system over here. But the equivalent, again, just for information's sake, if you feel like maybe it's really important, but it's not. What we basically do, we're taking connecting rod and we're making it into a two-mesh system basically, and that's all what we're doing. And then from that, we basically taking that idea, and then basically in our analysis now we include the force of the connecting, the force rod. I'm just taking an analysis a step further, but obviously the things we're doing here, especially this particular problem, incorporates two subjects. So obviously I like that. So yeah, so this is enough for that. So most of the exercises cover all of it done to here. Oh, there's two particular problems, and you'll see once you start actually practicing, it's all these kind of stuff. And obviously, if you can do those, you should be more than ready to we should be ready to write. Okay, so let's do this one, and then yeah, for the day. So it's gonna take some time, obviously. Again, I'll just have it here with what's the actual image. So again, for the first one, what we're looking at, it's either double acting, and if you see the word double acting, I'm just preparing the whiteboard. If you see the word double acting, particularly they normally give you two different pressures. And obviously one has not subtracted two pressures, and you see what I mean. Okay. So again, the one the turning mode and the crankshaft, and that's beautiful because now that's kind of off full circle. That's what you always typically in. Thrust on the bearings, and then now what I like is this acceleration of the flywheel if the power is that much, and the mass of the flower and the radial gyration. Why I'm throwing this in here because in the next chapter we'll be talking about flywheels and stuff. So you know, one wants to just kind of implicitly mention that is this. So again, it's horizontal, so you're not really worrying about the mass of the parts in terms of our setup. So, but normally it's just going to be FP equals FL minus FI. Same old, same old. What's really expand upon here is this FL, right? So I'm just there's some kind of pressure difference happening here. So if you have this double acting, obviously it means on two sides, and what they typically give you they give you two different pressures. Or what you really have to do is this. You're going to say FL is going to be you're going to have to basically take one pressure minus the other pressure basically. So you're going to say for the first pressure, it's 550. I think they give us one dimension. It has a bore of 250, if I'm correct. So let me just make sure that. Oh, So they say, let me just be sure. So the steam pressure on the cover side is 50, and on the crank side it's at 70, considering a piston rod diameter equal to 50. So let me just see here. It's a bore of 250 and a stroke, and yeah. So we have two different what is this? Two different diameters you have to be aware of in this case. So like in double acting one, typically there's one diameter, but in this one, they're obviously hinting that the piston rod is equal to well, yeah, it's equal to 50 more. So the first one, which is the 550, which will be the piston's diameter, right? The bore. And that's going to be 550 times pi over 4 0. Obviously this is just in relation to steam engines, but sometimes you don't even get like this kind of this, just making away. So on the other side they talk about, yeah, on this side of the thing, so this is the blue. Obviously this also can apply to compressors, by the way. Reciprocating compressor, that's the blue, that's that. And on the red side is where this piston rod essentially is, which is quite strange. Arguably one would think that, you know, the surface would be the same, but they've used the piston rod there. I'm not particularly sure why. Like I'm just maybe just tired now, whatever. And then yeah, we're just going to use 70 and pi over 4 and 0.05. Okay, so this is a smaller diameter. So that's how we're going to get FL. So I'm making you aware, if you see something like that, then you'd obviously know what to do. But for double acting, your it's double acting also. They'll tell you, like they'll say a piston rod diameter and also the what do we call this, man? The bore itself. So let's just quickly work out. I'm gonna work out over here and see what we get. So I'm just making you're just gonna subtract the piston thing, and this is obviously a horizontal end, so you need to be aware of that as well. So we don't actually have to worry about WR or the directions yet. Okay, so 70, 70. Okay, got that. Is this MPa or kilonewtons? Kilopascals. 0.05, and you should get 0.25, 70. I think, am I missing something here? I am, yeah, and I'm correct. I knew it. So, like I said, this is the blue side here, right? That makes sense. But on the piston rod side, what we have to do is take. So let me go the blue, the red here. So it is 550. I knew it, man. It's like this, and you get an answer of, just give me a moment, of basically, I'm gonna call it right, 27 kilonewtons. And then on the blue the area is not the same, so you're gonna say, I'm just gonna call this FL1, FL2 it's gonna be 70, and obviously now it makes sense. We have to sub and this is what I was thinking about the whole time. So we can say pi over 4. Obviously the diameter is 0.25 squared minus 0.05. This is what I was thinking now. Obviously it was on that side. The surface area is the piston itself is the rod. Yeah, now I'm happy. Now I'm gonna say it can't just be like that. It's just the fatigue is kicking in. And yeah, you should get around 3298 on the so-called 8672 newtons, and all we have to do is essentially subtract the two, and if I do that, my FL will be, that's 27 minus 3.29672, and 3.92672. Okay, 3.27. Okay, some mistake there. 3. Yeah, I get 23.7. Yeah, I think it's close enough. Book has a slightly different answer. Guys, do you guys all get that? On the double acting, piston rod, piston thing. Did we all get that? Thank you. Again, guys, from here it's simple. All we have to do is work our inertia force. Like I said, it's either one of these things you're always going to end up with. So m omega squared r, probably doing it over and over. So there's no problems. Should absolutely get it. But obviously, I like the vertical more. Obviously, now I have to find n, and let's go. Is a stroke of 400. So we know our rod is 200 and a connecting rod is 600. So it's 600 divided 200. And that should be 3. Always get a mark for that ratio. Once we have that, do we have any particular angle? Check it out. Nope. It seems when the crank has turned through an angle 45 degrees from inner dead center. So from what I understand, if it says from inner dead center, obviously I didn't even look at the analysis because I just maybe being too arrogant. So we have 20 degrees from top dead center, and that means I think it's coming down. Obviously in this case we don't only have FL, but FL is the difference between two different pressures, and obviously FI must be going that way because it's accelerating downwards. So always obviously start that, but like I said, most problems sit within that realm, but when it's vertical, I'm going to be playing around there. Obviously the mass of the reciprocating parts is given, typically always given, and it's 60 kilograms, and we have a rotational speed, and the rotational speed at is your rotational speed here, guys? 120 RPM, so it's steam engine, so it's not too fast. So I'll just do this. Radius was half the stroke, and half the stroke was 0.2. And we did say 45 degrees, not 20 degrees. I'm thinking of the previous example. Okay. Because 90 divided by, is just n? Yeah. So guys, just to recap again on this n. So we're just looking at two different pressures on either end. Here you got the exhaust steam apparently, and the high pressure steam, which is quite strange. You'd think that this should be higher. I honestly don't know. And then the area on this side will be the piston minus the piston rod will be on the other side, and the blue side it will be on the cover end, as it says. It will be 550 kilopascals. Okay. So let's get it Fi. In Bradley, maybe give it to me. Bradley's still around. Silas. All right, so let me just work it out. So just people's bedtime now, I think. 1339.86. That looks good. And yeah, once we're there, we basically at the end, we're looking for FP, which is a typical thing, and it's going to be 23.7 minus kilonewtons, obviously, minus this 1339.86. Let's quickly get that. 1339.86, and we get around 22.36 kilonewtons. 22.36 kilonewtons. Like I told you, The several ways to kill a cat. My particular favorite torque formula is this one. You'll see in the next chapter why. FPR, FP times R, sine theta plus sine 2 theta over 2. And I think that's in the formula sheet if I'm correct. Is it there? It's not even there. Yeah, see what I'm talking about. In the form. Yeah, I gotta rock up some new forms definitely. Yeah, so I know particular like that one. Or the other alternative is torque is equal to FP sine theta plus, the textbook uses this one, sine phi divided by cos of phi. And let's just quickly see what you get. 22.36 kilonewtons times that radius of 0. What's this guy? 0.2. Just make sure my torque form is right. It's a bit late now, so I must be careful. Yeah, torque should be right. Where are we again? Yeah, so we just work that out. 22.3 times 0.2 bracket sine 45 plus sine 90. Sine 90 is 1, I think, over 2 times 3, which is 6. And what is the answer? Is that correct? I get something different. 3897. So 22.36, sorry. Okay. Yeah, I get 3907. I don't think you missed a number. So it's sine 45 plus sine 90 divided by 6. You remember it's 2 times n. So n was 3. So if you do that, I'm pretty sure you're gonna get my, unless I add something extra. Highly doubt that. Crank was 0.2. Yep. And you should get 3907.51, which is fairly close. I've got 20. Yeah. Yeah. Let's check David. Okay, thanks. Just, I don't know if you guys can see that. That's how you find the torque. This is like a typical high end of. And then what they want now, the nice part is this. Is they want the thrust on the bearings and acceleration. So the thrust on the bearings, I'm not sure which force is that exactly. You know, I'm not sure. I think for double acting, it's something different. Yeah. Oh, yeah, it does actually exist, and I guess I didn't actually talk to that. Yeah. So let me quickly show you. Yeah, it does come out. Funny enough, it's one of those things doesn't really always come out, but it is there. So I'm not going to work that one out. Obviously, that's not like the point of what I was trying to show you. But I'm making aware that if you are working it out, then you do see. I wouldn't say focus on it, but yeah. So thrust on the bearings, if it does come out, it's just FP divided by cos phi times that over there. And obviously it's to do with your, it's just basically the thrust of the bearings. If it's you basically adding the angles. It makes sense now. The shaft bearings, you essentially. So that's not really of particular importance there. I mean, I wouldn't worry too much about that one, but I'm just letting you know it is there. You can get it. What I do want to touch on is obviously my favorite part of the question, which is on this, the acceleration of the flywheel, and if the power is that much, and the mass is that much, and the radius of gyration is that. So they were looking for the acceleration, right? So When you're hearing a radius of gyration, guys, one thing you must always be aware of, it's just telling you, it's going to tell you that torque is I times alpha. Right? That is what they're looking for here. Okay. And talked about the acceleration of the flywheel if the power of the engine is that much. So let's see how we're going to unpack this. First step, you're going to have to work I, and I, mass of the flywheel, and the mass of the flywheel 60. If you remove your formula times your radius of gyration 6 squared. Then you get your mass moment of inertia. Now I like these questions we incorporate these things. Okay, let's measure it. Let's calculate it, sorry, measure it. And you get 21.6. Remember the units, kilogram per meter squared. Right? Obviously, torque is next, right? But they say one must be aware that this is analogous to your what is this thing, your clutch thing, and we need to find the acceleration of the flywheel, and what you essentially have to do is subtract two torques here. So they say what they really call, they're saying that this over here. Okay, let me just show you anyway. Let's first work out the resisting torque, right? So that's on the engine side. It's P times 60 over 2 pi. And all we're really going to end up just doing is finding that torque, subtracting the other torque, the torque which I think the torque, how much did we calculate again? The 39 something from this new torque we got here. So yeah, that's basically all. And that's going to be 20 kilowatts times 60 divided by the 2 pi times n, and the speed was 120. So it's basically like a clutch typical problem, because what's happening is that, you know, the flywheel essentially absorbs, you know, what is that torque value? T times 60. Yeah, it's 1591.55 Newton meter. And like I said, all you have to basically do is say it'll be this torque, and it'll be the 39. I think we got 3907.51 minus 1591.55, and all we must just basically do is divide that by 21.6, and that'll basically tell us the acceleration of the flywheel. Yeah, that's basically all. So it's one of those other questions. It's been a long day. Yeah, is that correct? I get a different answer though. Oh no, I don't actually. Is this in kilonewtons, right? Am I missing something there? Yeah, no, that's right. Is my, oh yeah, this is not my bad. This is 21.6. Sorry, 21.6. And you should get around 107.2 per second squared. Oh, okay, guys. I'm still there. Missing Silas, must check. Any questions, guys? Yeah, this is a big problem. Yeah, thank you, Jason. And afterwards, the last problem, don't take too long. Just the first part of it takes a while. Who else is still here? Bradley, are you still there, Mr. Matoso? Right.
Yes, sir. I'm still here.
Oh, great. Yeah, so that's that example. There's an example like that in the textbook as well. I think it's number, make sure you go over it. Yeah, and obviously there is this crankshaft in the bearings, which is particularly new. Not very common though. That's example 17, where they ask you determine the angular acceleration of the flywheel. So you must be aware of that. If they don't give you a resisting torque, obviously you just use it to you there. Yeah. So, and be aware of double acting and things like that. But most is obviously focused on, the easy kind of stuff. Like I said, you can make it. It's easy to make it. It can be really creative with such a problem. Okay, guys. This is, I guess, a fairly advanced example which incorporates a lot of things. And then you head off into the last one. And the last one is basically one where we include a thermodynamic cycle. And this is what I've been probably was keen to do the whole of the semester. Seeing that obviously I've taught. Ooh, look at that. Beautiful. You've got an old diesel cycle. And obviously that means I can incorporate any diesel cycle with different parameters, and yeah, you can have. Obviously, this question is a big question. In comparison to gas turbines, like a 30-mark question. But it's definitely you can get it. Also procedural, but one must know what they're talking. Okay. So, what is the question one from us? At the end of the day, I said a vertical double acting steam. No, this isn't sorry, I'm the wrong one now. So I meant, yeah. A vertical cylinder acting diesel engine, a cylinder diameter of 300 and stroke of 500, connecting rod 4.5 times the crank length, right? The engine runs around 80 RPM, very like a diesel engine. The mass of reciprocating part is 280, yep. Compression ratio 14, pressure is constant to the injection of the oil for a tenth of the stroke, yeah. If the compression expansion follows the PV, 1.5 is constant. The crank effort, the crank pin effort, and I think the crank pin effort is going to be what? What is the crank pin effort again? That's I'm not even sure what that is now. What is my crank pin effort? Is that my piston effort, right? Understand the thrust on the bearings, turning moment as well. And yeah, the crank pin effort would be one of those, where's the previous whiteboard now? So we must be aware of that as well. So it is actually does come up again. Yeah, not really. Crank pin effort, which is basically that one there, and your thrust on your bearings there. Okay, let's get back this. Where's my this one here? So that's what they want here. So it does come up again. Okay. Oh, let me just get it from the actual thing. Yeah. Yeah, but it's just if you have your FQ and your angles, it's there. But I obviously one needs to also remember. Yeah, I really have to make a proper formula sheet. I'm realizing now with all these stuff here. It's a lot of stuff to remember. Yeah, so one is your crank pin effort, which is the one you see there. The F because sign, two angles, and the other one is one of the crankshaft bearing. So that's two different forces basically. And it's saying the component, yeah, basically, okay, I'll show you, I can show you where it is. And I actually didn't realize, we actually discussed that. But I'll show you exactly what it is now. Because apologies for not, because I mean, obviously other questions are addressing it, so yeah, I mean, I think that's why I kind of overlooked it. But it's these forces here. Okay, it makes sense if you think about it actually. So if I open it up for you, they're looking for these forces. So that's FP, right? That makes sense. It's on the crank pin itself, right? Well, that's the crankshaft bearing. That one there, and there's a FT, which is that one over there. So that's the two basically what they're looking for. So obviously we've been doing FP, we've done FQ, but there's an FP actually, and there's also an FT force. So there is actual other forces we've actually been overlooking, or I've been overlooking rather. I'll just leave it there, maybe for later on. But it's obviously there's its own formulas, right? Anyway, so how do we start this? Let's look over here. It's a vertical engine, and obviously we have to now think about more. So vertical engine, and how are we moving here? It says, just tell us where we are. Yeah, it says from inner dead center during the expansion stroke. So if I look at that, so I'll just draw my post. Let me just draw a line here. So this is probably the most difficult example you can get. Just letting you know. Yeah, so that angle there, I think, something like that, 45 degrees. Stop dead center. Got your piston over there. Expansion, that's FL. That's expansion is moving down. Therefore, FI is going this way, FL is going that way, and your weight is going that way. So FP will be equal to FL plus WR minus FI, if I remember correct. It's going expanding, so it's going down. Yeah, so FI is going up. Yeah. So I think that's what we're heading towards here, right? FI should be negative, and we should be adding those two as per usual. Okay. So where is all the work really? Work is FL. FL is now we need FL, and all they give us is basically a compression ratio, and they've given us the compression ratio and the what do you call this, the PV law. But obviously we are aware of the processes. Hope for the guys who are not rusty with thermodynamics, obviously the guys who've done it, this is going to be easy for you. Here we have our compression. I'll write it over here. 1 to 2 is compression. What can we call it? What we typically call it? Isentropic compression, right? Maybe. But in fact, it's not isentropic compression, it's a polytropic now. So 2 to 3, constant pressure, heat. What is this? Heat addition. 3 to 4 is your polytropic expansion. And of course, 4 to 1 is your heat rejection, right? So heat rejection. So that's your exhaust basically. Exhaust, this guy's a combustion. Okay. So imagine this is some real level stuff here. Compress two kinds of knowledges into one. So FL is the main one. So we're gonna have to really expand upon FL. So all we're basically looking for, guys, if you think about it, we are just looking for. So the only problem here, this question, which I'm kind of annoyed for, is that they're telling you that it's they really made it like they say it's 1/10 of the stroke. So they're really being a bit unnecessary in terms, where it's positioned. So I think I'm not going to make it 1/10 of the stroke. What I'm going to say is I'm just going to work out the pressure from. Oh, but thing is, it makes sense. Yeah, it makes sense. The reason why they say it's 1/10 of the stroke because it can't be because the pressure will be the same essentially on the cylinder. So they basically chose an arbitrary point where you can have some kind of pressure difference. That's all it really is. Okay, so let's start on the thermodynamics. First, do you remember your laws? Really, when last you do thermos 3. I know the other guys, they have done this.
I think Thermos 3 was in 2018. So.
Yeah. And we do thermos 3 or heat or thermos 2018.
Yeah, that's
okay.
correct.
Yeah, so anyway, we were experts, so we know how to find P2, P1, compression ratio to the power 1.35. I've got a lot of top dogs in this game, so you have to worry. So the first pressure obviously is given. Suction, that's 100 kilopascals, guys, and compression ratio is 14. Yep, 14 to the power 1.35. Right, you're gonna get 3,525 MPa. Okay, that's that. What is next? Like I said, you want to find all the pressures and stuff. So we have P1, P2. I think we need to find volumes as what I can see over here. Yeah, we need to find the volumes of each of everything basically. Yeah. So pressure, volumes, and temperatures. No, not temperatures, just pressure and volumes here. So we need to get P and V's, not T's this time around. We don't need pressures. So we don't need temperatures. Okay, so after this, our compression ratio is V1 over V2. And looking at here, it says we have a stroke length and a cylinder diameter. And we should be aware that V1 is equal to your V stroke plus V clearance over V clearance, right? I think that should be fairly familiar to everyone. I think so. And if we can just simplify this, Mr. Matoso, what do we get? RVC equals VS plus VC. We're looking for VC really, so maybe we should just, how can I get VC on my own? Okay, I bring it over RVC minus VC, yes, and then what is this one here? Is this going to make sense? Take VC as a common factor, so we have R minus 1 over VS, and then we have VC is basically equal to VS compression ratio over that. I think that's right. So stroke has to be worked out as pi over 4. I'm assuming you all know what the stroke is here. Is 0.3 squared times 0.5. Divide that by compression ratio is 14 minus 1, and we can get VC. And remember, VC is also V2, right? Yeah, that should be V2. Okay, we're nearly there, I think. The hard part is just the and 14 minus, and I get an answer of my V2 is equal to VC is 2,71. It should obviously be small 87 times 10 to negative 3 meters cubed. Students, are you following? Are we still there? Are we still there?
Sir.
Yeah. Yeah, you must just bear with me. Yeah, okay. So once we have V2, what they state there, they say that, so obviously we have to go to a process now. That's between 2 and 3, right? That's a combustion. But they say that for us to find V3, what they've done is they say V3, okay, is equal to V2 or VC, right? Plus a tenth of the stroke. So that's the key there, right? So I could change this value, literally just change this value to 120, 130, whatever. So tenth of the stroke. So you take that 2,7187 plus your stroke, right? And your stroke was, I don't know what your stroke, stroke was pi over 4 times 0.3 squared times 0.5 divided by 10. Right, so let me work that guy out. That's going to be nearly there. This is just the thermodynamic part of it. This might just come in the reassessment, if you ever see the reassessment. I deliberately, this is a very important one. This one is like the ultimate problem. 6 I guess 4.5 meters cubed, right? Well, not meters squared. So that is V3, right? So V3 is basically there, right? So remember, it is a function of the stroke. But what they want that V4 prime, right? And For us to get V4 prime, it seems, what do we have to do? Okay. So V4 prime, just check this out. It's also V2 plus pi over d squared times x. Right? We need to find, right? So we need to find where is the piston along its length over here. And this x, if you remember the x is equal to r L, no, R, sorry, bracket 1 minus cos theta. It's extremely beautiful, I promise you. Sine squared, no, sine squared theta over 2 sine squared over this. Obviously, we need to calculate x. Once you have x, we're going to get this V4 prime. So like I said, where is the piston now? Because we need a new volume. This is another volume if you think about it. And that's going to be 0.25, right? 1 minus cos 45. Change one angle, the whole game is changed. Again, plus sine squared 45. And I don't know if you have n. Have you worked on n before? No, we haven't worked on n, eh? And n is, they state there, at 4.5 times, so it's L over R is 4.5 basically. So they gave you some liberty there. Oh, not working that out. And once you work out this, let's see what you get. So I mean, you can change one value, and it's just it's madness, really. It's beautiful actually. If you think about it, it's crazy. Now we've got this far, we can integrate two stuff. You know what I mean? It's really, I think it's quite fascinating, and you should get an answer of. So it's telling you how far the stroke. It's like 87 mil of the stroke basically. A total stroke length was given as 500. So it's like 87 apparently. So once you have that V4 meters cube, right? No, that is meters. You got to find V4 prime, and it's simply again just adding the clearance volume to that. So that's going to be V2 plus whatever this is. So I did right on top. So this is going to be at 2,718. 2,718 7 times 10 to negative 3 plus I mentioned to you was that new volume basically. It's this. Okay, so that's D, and that's going to be 0.3 squared. Obviously it's not the whole stroke now, it's just a small fraction of this 7, and you should get an answer of around 0.8 times 10 to negative 3 meters cubed. Man, so welcome to S5. Yeah, welcome to S5 now. Things have changed drastically. Man, look at this. What's going on here? The parents will be proud. So finally, once you've got that V4 prime, which is basically somewhere along here, right? All we're doing is going to find that P4 prime, and we do exactly the same thing. So we know P3, V3, or we are experts. Okay, let me just write it out for doing thermals now. 1.35. Obviously, we're expecting a decrease in pressure. V4 prime, and obviously this is now P4 prime, meaning is P4 exactly. So we just basically find P4 prime, and P4 prime is just going to be P3. P3, we found the previous pressure, didn't we? Something odd, megapascals, 3.5259. 3.2, so 3.2, 3.5, 3.2, 3.559, if I'm right. And obviously, you have to divide by V3 or V4. It's to the same power, 1.3. That's why we found that V3, and that V3 was initially 6,24 something, 6,245 5 times 10 to the negative 3 divided by, what is this guy again? What is this guy? 8.8 times 10 to the negative 3. Okay, my P4. Guys, once you've done this, it's over basically. 3, 5, 5, 9. This is minus. I'm hoping you still around to quickly calculate for us. Don't know who's still around here.
Yes, I got 2.197.
Yeah, I get 2.2 though. 2.197. That's fine, yeah. 2.197. I got 2.2. I'm gonna make a mistake here. 2.197. Yeah, I'll accept it. Yeah, that's good enough. Okay. And guys, once you find P4, all it really means is that now you can characterize your is it your FL? Your FL will basically be P1 minus or P4 prime, sorry, obviously it's higher pressure. P4 prime minus P1. You still have the same diameter, pi over 4 times 0.3 squared. That's a force, right? And if you do that, you'll get 2,19. Is it megapascals or kilopascals? That should be kilopascals. This is kPa. This must be kilopascals, eh? Remember, it's after expansion, so there's no way it can be. What is this guy now called? It's 2.8.8. What is it? Is it MPa or kPa? Yeah, that looks like it's fairly high pressure, 2.2. Yeah, that's yeah, it's MPa. Yeah, that's quite big. Okay, so yeah, it's minus. Okay, so this is not obviously. This is definitely not right. It is MPa. It's quite a. It's not. It's P4 prime. It's not P4. Sorry, yeah. So it makes sense. So the pressure's dropping from 3 to 4. So 3 was 3. It's P4 prime. Yeah, it makes sense. It's not exactly on the dot. So yeah, that's minus 0.1. This is MPa times 10 to the power 6 times, of course, this pi over 4 times 0.3 squared. 2.197. You've entered the domain of exclusive intelligence of far. A few has come to see thermodynamics and mechanics of machines meet and understand it at the same time. I get this answer. And the rest, I think you guys can figure out on your own. But be very aware of this problem. This is a straight 30 mark problem. You will see it, I can assure you. Not in test 2 though. Yeah. Any questions before we close? Yeah, that's a good way to end the day. Mr. Manis, Mr. Batoso, Mr. Mkhangeni, Mr. Kawa, Mr. Doyle, Tepo, Freeman, Linukushe, Muchanka, Silas. Any questions? That's the guys who soldiered on. Sure. Sure.
Yeah, it was just a heavy day.
Yeah. So how do you find this problem? I think it's fantastic, eh? Heaviest, yeah, it's crazy. Yeah, it's dope. I really like it. I really like it. Like, I wish I could assess on this level all the time. Like, this would be like this is challenging. I mean, just think about it. It's from that talk we can work power. Imagine all the stuff we can work together. But guys, you know what? I commend you for staying throughout the day. Obviously, all pay in the tests and your final mark. Next week, we're starting a new chapter, and I aim to complete that chapter. So, yeah. So, I don't know. I don't think I'm gonna have too challenging. That's it. Yeah, a lot of mistakes can be made, yeah, but it's just nature of the game. Question like this, I can soundly fault you on making a mathematical mistake. Mr. Kiefer is even gone. Yeah, I'm gonna have to probably squeeze in trans very long, yes. Squeeze in transmission lines probably early in the week, and then do energy systems in one shot. Energy systems are not that difficult, so it's actually quite easy. You must just understand what you're doing. It is around a few problems. It's like 23 problems. Obviously, you won't cover all of them. We'll cover the ones we need to cover is around, yeah, to cover around 5 or 6 of those problems, which will give you an idea of what you need to do. I just need to, yeah, then gearing. I don't know how we're gonna. I need to do gearing as well. So, yeah, but it's very important. I'm saying to you here, vertical engine. Make sure you go over it. Make sure you understand it very well. And compressor. Very key. Make sure you can find your thrust. Make sure you can find your thrust. The F and the FQ. Make sure you and obviously there's just some new stuff which I'll include, and I'll see who's the crank pin effort and the thrust and the crankshaft bearings. I might throw that in as well. Just extra stuff. Yeah. What I'm going to be doing, I'm going to somehow have to work and make work on a formula sheet of some sort. Extra formulas basically, because obviously there's a whole lot of formulas. But this question, don't worry about it now. For the next test, for the final, we have to probably, but clear that we've done it. And like I said, this question can go anywhere, guys. Literally, I can change one compression ratio change. I can make it 1/5. Make the compression ratio 22. Change the angle. Like I said, the creativity comes by itself here with all these questions. Remember also, when is maximum velocity, find those angles, how to find, make it 0, all of those things. It's all there together. Guys, thank you. And yeah, I won't be really available tomorrow to finish up setting final exams, but I will see you on Friday. We'll conclude heat transfer and air compressors. And air compressors will conclude the other week, but yeah, we'll start on it definitely. And yeah, just well done on getting through this day. And enjoy the rest of your day. And let me know if you need anything, try to assist you. Okay, guys, cheers and have a good evening.